Hello everybody, and welcome to our video on the definition of the derivative. So the derivative is a pretty straightforward idea. It's a pretty natural problem to want to solve, which is the question of finding instantaneous rates of change. So the most common thing that we usually consider with instantaneous rates of change is change in position. So if we're looking for the instantaneous rate of change of position of an object, that refers to its velocity. So how fast is the position changing? So we'd be talking about velocity. But there are many rates of change in applications. So one you might consider is marginal cost, the rate of change of cost to produce an object. So we're just going to talk, we're going to start out thinking about this idea of average rate of change. And for now, if it makes it easiest to consider, then you can focus on thinking about this as being the velocity in relation to a position function. So let's go ahead and think about, okay, how do we find average rate of change? Well, if we take a look here at this graph, we've got a function and we've got a y value f of x, y value f of t, and the corresponding t and x values on the x-axis. So when we look at this f of t minus f of x over t minus x, this is the change in f divided by the change in x, which is exactly what we mean when we say average rate of change from x to a. Now, we can also think of this as rise over run. It's the change in y over the change in x. So that tells us something very interesting here, that the slope of this line between the 2 points on the graph is the average rate of change. The slope of the line is the average rate of change for the function over that time period. Now, one thing I'll point out as a little bit of an aside here is that I've written this as f of t minus f of x over t minus x, and given that f of x is the larger value, it might be natural to get a little tripped up by that. Hey, shouldn't we take the bigger thing minus the smaller thing? But it actually doesn't matter, because if I take negative f of t minus f of x over negative t minus x, I'm really, if I put negative in the top and bottom, I'm multiplying both the top and bottom by the same thing, and I would get f of x minus f of t over x minus t. So in other words, these two things are equal. So there's really no difference between saying f of t minus f of x over t minus x and f of x minus f of t over x minus t, as long as we keep the x's together on the left side and the t's on the right, or vice versa. I've written it in this form just because it's going to be a little more convenient when we manipulate this expression a little bit. Okay, so again, this expression, f of t minus f of x divided by t minus x, it's the change in f divided by the change in x, so it's the average rate of change, or it's also the slope of what we call the secant line between the 2 points. Okay, so how can we get instantaneous velocity from this idea of average velocity, average rates of change versus instantaneous? Well, when we say instantaneous, we mean at a single moment in time, and this average rate of change function requires that we have 2 points in time to sample. But if we want to take the instantaneous rate of change, that's not going to work. We need just one. So the way we do this is we think about what happens when our amount of time shortens. So we get a smaller and smaller interval between t and x. So let's look here. We've got these 3 secant lines drawn between these 3 sets of points, or these 3 points t and this point x. And so what we see is that as we take points closer to x, the slope of these secant lines is changing. So our averages are being taken over a shorter length of time. And we want to imagine what happens to this average rate of change as the amount of time going by shrinks towards 0, right? That's the idea here. So this is why the tools of limits are so important in calculus, is because we can build this idea of rates of change using the structure of a limit. So we ask ourselves, okay, what happens as t approaches x? That's a limit. So we take the limiting behavior as t approaches x of f of t minus f of x. And what we see is that the slopes of these lines approach the slope of this line here, this line that touches the curve and sort of hugs the curve. We call this the slope of the tangent line of f of x. So this is the instantaneous rate of change at x. This is what we define as the instantaneous rate of change of f at x. Now, as we've seen in some previous work, sometimes changing the form of the limit, expressing the limit in a different way, can make it easier to solve. Now, we're going to take a look at a different common form for this instantaneous rate of change. We can substitute h equals x minus t. So then what do we get? Well, since t is approaching x, then that's going to imply that h approaches 0 because h is x minus t. I should have put t minus x there. Let me correct that real quick if I can get my cursor to pop up. That should say t minus x. So then when we make this substitution for t minus x, our denominator becomes just h, and h is approaching 0. But now, since our limit isn't going to involve t, we make one more little substitution. We take if h equals t minus x, then t equals x plus h, and we just replace t in our formula with x plus h. So this formula is the same thing as this formula, just in a different expression. And sometimes this version is a bit easier to work with, but sometimes this version is easier to work with. It depends on the individual problems. You should be comfortable working with both versions of the definition. Okay, so instantaneous rate of change. Well, this is what we call a derivative. We say that the derivative of the function exists if either of these limits exist. And so now let's formally define the derivative. The derivative of a function f denoted by f prime is the function defined by f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x divided by h, provided that this limit exists. So, to be clear, what is this derivative function? It's a function that tells me the slopes of the tangent lines at each point along the curve. All right, that's what this thing does. So we're going to go ahead and do an example of this by first finding the derivative of f of x equals 2x squared plus 3 at x equals negative 2. So we just want to apply the definition here. And it's always a good idea to write out the expression for the definition that you're going to use. And here we're using this version of the definition. All right, so we've got f of x plus h minus f of x all over h. Now, what I'm going to do is, since I'm taking f of x plus h, we have to replace our entire original input, x, in the original function with x plus h. So just make sure you're careful about that. Anywhere you add an x before, you need to put parentheses x plus h. So this is 2 x plus h squared plus 3 minus f of x, which is 2x squared plus 3. Again, we need to make sure we put a parentheses here because this negative applies to the whole function. It needs to be distributed all over h. And now we're going to solve this like we would any old limit. So we're just going to go ahead and work out some algebra here. I'll go a little bit quickly through this part. X plus h squared gives me x squared plus 2xh plus h squared. So 2 times that plus 3 minus 2x squared minus 3. All I've done is distributed that negative there. Now I'll distribute this 2. Okay, now that I've done the distribution, let's see what we can cancel. We've got 2x squared and negative 2x squared. We've got 3 and negative 3. And so now let's go ahead and rewrite this limit. So now I'll factor an h out up top. Now I can cancel that discontinuity with h. And now when I evaluate this limit, I have a continuous function, so I can just plug 0 in, and I get 4x. But the question didn't ask for the general derivative of f of x, even though that's what I found. It instead asked for the derivative of f of x at x equals negative 2. So f prime of negative 2 equals 4 times negative 2, which is negative 8. So that's our answer for this one. In other words, this is the slope of the tangent line to the function f of x at negative 2, or the instantaneous rate of change of the function at x equals negative 2. Okay, let's go ahead and move on here to another definition. If f prime of a exists, then the equation of the tangent line to the graph of the function y equals f of x at the point p equals a f of a is y equals f prime of a times x minus a plus f of a. Now, I often see students get a little tripped up on this idea. I think because the notation is a little bit different. But this is your old-fashioned point slope form. Y minus y1 equals m times x minus x1. We've just changed the notation a little. If I move y1 across, I get y equals m times x minus x1 plus y1. So all we've done is taken our point slope form and moved y across. And now all I'm doing is just replacing the corresponding parts. F prime of a is the slope of the line. F of a is our y1. A is our x1. So that's all I've done here is just rewritten point slope form in the notation of these functions and derivatives. Okay, so with that in mind, let's go ahead and take a look at this second example. Find the equation of the tangent line to f of x equals the square root of x at a equals 2. So in other words, to find the slope, we need to find f prime of 2. Now, what I did before was calculated the general derivative function using the definition. And if I know that I'm going to need to look at several, at the rates of change for several values of x, generally that's the better thing to do, because then you get a simple function that you can plug into repeatedly. But we don't have to do it that way. In fact, there will be cases where we need to actually use the definition at a single point for some reason or another, as we'll see later. So, but in this case, just to kind of warm up to that, I'm going to write this f prime of 2. Instead of finding f prime of x first, I'm just going to use f prime of 2. So if we take our definition, instead of x, we just write 2. So f of 2h minus f of 2 over h. So this is the square root of 2 plus h minus the square root of 2 all over h. And so now I just need to evaluate this limit to find that derivative. All right, so we've seen things like this before when working on limits. We multiply by the conjugate. So since these are conjugates, when I multiply them, the middle terms cancel, or the middle and the outer terms cancel, and we get 2 plus h, the square root, times itself. So I get 2 plus h minus the square root of 2 times square root of 2, which is 2, all over h. So this is the limit as h goes to 0. 2 plus h minus 2. Oh, I dropped a term. I lost that little part from my denominator, the square root of 2 plus h plus the square root of 2. There we go. 2 minus 2 is 0, so up top we're just left with h over h times the square root of 2 plus h plus the square root of 2. H over h is 1. So now we have 1 over the square root of 2 plus h plus the square root of 2. Now my discontinuity in the denominator has been canceled, so now I can just plug in h equals 0, and I get 1 over the square root of 2 plus the square root of 2, which is the same thing as 1 over 2 root 2. Now, I would be fine with this generally, but most of the time you'll see it, so it's worth practicing. You'll see it rationalized by multiplying by root 2 over 2. And then we would get root 2 over 2 times 2, which is 4. Either of those answers would be fine to me, though. Okay. Well, that's it for that one. Oh, wait, that is not it for that one. That's just the slope. We have to actually finish the rest of the problem. So, remember, we need y equals f prime of a times x minus a plus f of a. So I have f prime of a, that's f prime of 2. So this is y equals the square root of 2 over 4 times x minus 2 plus, and now we need f of a, but f of 2 is just the square root of 2. Now I am going to simplify this expression for the line a little bit. By distributing this out, I get the square root of 2x over 4 minus 2 root 2 over 4 plus root 2. Okay, so 2 over 4 is 1/2. And if I have, oh, that should have just been root 2, not root 2 over 2. Now if I have an entire root 2 and I subtract half of a root 2, I should get left with a positive 1/2 root 2. So in other words, if I rewrite this a little cleaner, y equals root 2 over 4x plus root 2 over 2 is the equation for our line. All right, so that's it for example number 2. Let's go ahead and move on to examine a little graph problem here. Sometimes you'll see a problem like this and it could trip you up a little bit, but it's actually really quite simple. So use the graph to determine the equation of the tangent line to the function at the point. What we see is we've been given the curve and we've actually drawn the tangent line. So in this problem, you've been given 2 points. Well, in order to find the tangent line, oh, I need the derivative at 2, but that's just the slope. And I can get that from rise over run between these 2 points, right? So y2 minus y1 over x2 minus x1, that's 1 over 2. And I've already got the point 2, 1 as the center point. I shouldn't say center point, but the point where the tangent touches the curve. So we get y equals f prime of 2 times x minus 2 plus f of 2. So y equals 1/2 times x minus 2 plus 1, right? F of 2 is 1. And now we'll distribute a little bit. That gives us x over 2 minus 1 plus 1. So that gives us a really nice simple y equals x over 2. Okay, now let's go ahead and introduce another notation. So far we've been using the prime notation. So this is also known as the Lagrange notation for derivatives. But oftentimes this notation leaves a lot to be desired in terms of clarity when we get into certain specific topics. So for example, a rule known as the chain rule for derivatives becomes quite a bit more confusing in my view when you're using prime notation, as it obfuscates some of the details that you need to stay aware of. So an alternative notation is that of Leibniz notation. So we're going to introduce that here, and gradually as we go through the sections, I will start leaning more and more into using Leibniz notation instead of the Lagrange or prime notation. So we often denote the expressions f of t minus f of x and t minus x as delta f and delta x. So this is delta f, and this is delta x. That just means this delta should be thought of as change in f, and this should be thought of as change in x. That's what we're using that delta to represent. So in this way, we can denote our derivative as the limit as t goes to x of f of t minus f of x over t minus x equals the limit as delta x goes to 0 of delta f over delta x. So again, t minus x as t approaches x, this approaches 0. So that's all we're saying. Delta x goes to 0. So in using that notation for these changes in f and changes in x, we will often write, instead of f prime of x, we will write df dx. So this should be read as the change in f over x, or the change in f with respect to x, or the derivative of f with respect to x. So there's a lot of different ways we can express that are equivalent, but we may also use dy dx interchangeably with df dx. A lot of times you'll see that if you're using y instead of f of x. So in any case, we'll go ahead and use this notation for some of the problems we work on now, but there's really no difference. We're just going to notate, instead of saying f prime of x, we're just going to say df dx and start getting used to that notation. Okay, so before we get into those problems, though, we'll deal with one more graph. So that graph represents the population of a bug species over time. Rank the points from least to greatest in regards to the rate of change of the population. So here I'm just looking at what's the smallest rate of change, what's the biggest. So we'll start by looking at, okay, well, which rates of change are negative? Well, r and q are both negative. And I would say the slope for r, the tangent line at r, is steeper than that for q. So I would say r is the lowest rate of change, right? It's the smallest number. And then q. And then p and s have positive rates of change. P is a steeper slope than s. So I would say s is next, and then p is last. All right, so just keep in mind that what we're describing with these derivatives is these rates of change at the point, and inherently, that's telling us something about the behavior of the curve. And essentially, where this tangent line is pointing is where the curve is going at that moment. All right, when I look at r here, this curve is going in the direction of r at this point, and then, yeah, it curves back up afterwards. Okay, so let's move on. We'll talk about velocity, and we'll use some df dx notation here. So recall that from a time a to x, that should say time t to x. Another typo. Sorry, folks. That should say t. Recall that from time t to x, the average velocity equals the change in position over the change in time, or f of t minus f of x over t minus x. So this was all our alternative version of the derivative. So this is equivalent to our definition of the derivative. And here we've got, we're just denoting it as df dx equals the limit as t goes to x of f of t minus f of x divided by t minus x. So here, in example 5, if a ball is thrown up in the air with an initial velocity of 55 feet per second, then its height is given by h equals negative 16 t squared plus 55t, where t is in seconds. Find the velocity after 3 seconds have passed. So here, what we want to look at is the derivative of h with respect to t. So that actually means we have to write our definition a little bit differently. But what I'm going to do here is actually look at just the specific case when t equals 3. So I'll talk momentarily about the advantages and disadvantages of Leibniz notation. So for Leibniz notation, the biggest advantage is that it allows you to keep your variables straight once you start having multiple variables involved. So it tells you, I'm taking the derivative of this variable with respect to this other variable, which is going to be important if you have multiple variables or variables inside of another secondary function, as we'll talk about with the chain rule. But its downside is that because it's not function notation, we have to maybe do some things that are a little awkward when we want to denote a specific value that we're taking the derivative at. Like here, I've said at t equals 3. So that's a little bit of a downside, but that's not that big of a deal. The trade-offs are going to occur in either direction. When you use prime notation, you lose some information about what variable you're taking your derivative with respect to once you start dealing with multiple variables. So with that all being said, let's go ahead and tackle this derivative. So here, we're going to be taking the limit as t approaches 3 of h of t minus h of 3 over t minus 3. So this is the limit as t approaches 3 of negative 16t squared plus 55t minus negative 16 times 3 squared plus 55 times 3. All over t minus 3. Now nothing's being applied to this parentheses here, so I can drop this parentheses and write just negative 16t squared plus 55t. And here, negative 16 times 9, so that's going to be 144, so negative 144 plus 55 times 3, which is going to be 165. So 165 minus 144 is going to be 21. And then there's a negative being distributed, so that'll be negative 21. Okay, so what I'd like to do is factor this and try to cancel the factor of t minus 3 on the bottom. Now, there are a lot of different ways you can deal with factoring quadratics with leading coefficients other than 1. But in this case, I have every reason to believe that t minus 3 is one of those factors. So what I'm going to actually do is, it's kind of cheating here, but not really. I'm just going to go, hey, I'm pretty sure t minus 3 is a factor. Let's guess that t minus 3 is a factor and figure out if what the other factors would be. Well, whatever's here needs to multiply by t to give me negative 16t squared. So that would be negative 16t. And whatever's here needs to multiply by negative 3 to give me negative 21. So that would be plus 7. So that's my guess. Now, let's make sure that that's actually correct. So I do the multiplication. I get negative 16t squared. I get negative 21. And then for the inner, I'll get a negative 48t plus 7t. Or sorry, that should be... 48. There should be a minus in here. That should be... Did I make a little mistake? This should work out. Let's just check and see if I've got a little mistake in here. Okay, we've got negative 16t. Okay. Oh, yes. The two negatives cancel. That's a positive 48 plus 7t. So that's a positive 55t. I did not make a mistake. I just forgot how... Well, I did make a mistake. I forgot how to multiply. There we go. So I guessed my factor correctly. Again, this is just a nice little shortcut when you're working with this kind of problem. You're pretty confident that one of your factors is going to be that. So we checked it. It worked. So we can cancel. And this gives me the limit as t goes to 3 of negative 16t plus 7. So this is a continuous function, so I get negative 16 times 3 plus 7. So this would be a negative 48 plus 7, that's negative 41. And since we're talking about velocity, and this was feet per second, right? So that's feet per second. Okay, so that's it for this one. Let's go ahead and move on. Now we want to determine if the derivative at 0 exists for this function. So now since this is a piecewise function, and it's defined separately at 0, I have no choice but to use the definition with x equal to 0 built into it. I can't do this as f prime of x and then plug in 0 after, because this function is defined differently outside of x equals 0. So we got to be a little careful about that. But that's fine. It's not a big complication. And I'll go back to using my limit definition with h. So this will be f of x plus h, or that should be 0 plus h in this case. F of 0 plus h minus f of 0 over h. And f of h, because f of 0 plus h is really just f of h. H is non-zero, right? When we take a limit, we're not looking at what happens when h is equal to 0, just what's happening everywhere near 0, how it's approaching. So when I look at h not equal to 0, I use this part of the definition. This would be h times cosine of 1 over h minus f of 0, which is just 0, divided by h. So this is the limit as h goes to 0 of h times cosine of 1 over h. Now, 1 over 8, that h canceled. That should be all over h. All right, let's write one more step here for clarity. So now we've got the limit of cosine of 1 over h. Now this 1 over h, when h goes to 0, this is going to plus or minus infinity, depending on if we're going from the left or right side. But we got to remember this cosine function, it's a wave. Actually, that's the sine function that I just drew. Cosine would be like this. And so if I'm just taking my input going to infinity, these y values are cycling across values from -1 to 1. They're never going to approach any fixed value. So we would conclude that this does not exist. Okay, so let's go ahead and take a look at this one. Determine where f of x is equal to where the function f of x equal to the absolute value of x is differentiable. Okay, so first of all, we got to recall that the absolute value of x is defined as a piecewise function, x if x is positive or 0, and negative x if x is already negative. So the crossover point is the concerning point of the absolute value here. The function y equals x is differentiable. That's very easy to work out with the definition of the derivative. I'm going to skip that part, right? But this is definitely differentiable for x greater than 0, which is, again, a much easier derivative to take using our definition than the examples we've already done. So we'll skip that part, and you can try that on your own. And here for negative x, again, it's going to be the same thing, right? But you'll get a negative answer because you're multiplying everything by -1. So this is differentiable for x less than 0. The problem occurs at 0, where we will have to take limits from the left and right hand side to determine if we get the same value. So let's take a look at that. So if I take the limit as h goes to 0 from the right hand side of the absolute value of x plus h, but we're looking at 0, right? So 0 plus h minus the absolute value of 0 over h. Since we're taking h approaching 0 from the right, that means h is positive, so the absolute value of h is just going to be h. And h divided by h is 1, so this is the limit as h goes to 0 from the right of 1, and the limit of a constant is just the constant, so we get 1. But if I take the limit for this derivative from the left-hand side, the absolute value of h, since h will be a negative number, is going to be negative h. So we get negative h over h. So this becomes the limit as h goes to 0 of -1. Which is equal to -1. And of course, 1 is not equal to -1, so the derivative does not exist at 0. Okay, so where does this problem come from? Well, let's look graphically at what the absolute value looks like. So the absolute value looks like two straight lines with slope -1 and 1. So what we see is that any pair of points on the left-hand side with 0 is always going to have slope -1, and any pair of points on the right-hand side with 0 is always going to have slope 1, right? And so when you take those limits, you're never going to get them approaching the same slope value. So there is no tangent line at that point. So this we call a corner. So let's ask ourselves a little more generally. What situations can cause a function to not be differentiable? Now this might not be an exhaustive list of functions, but here's some common situations. If we have, like what we had before, a corner, or we might have what we call a cusp. So that might look like this. It looks a lot like a corner, but it's, instead of two straight lines, you have like a curve where the direction of the curve changes at that point. So the cusp could go that way, it could go, you could flip it upside down, etc. And another type of situation you might have where a derivative could not exist is a function with some like wild behavior. So maybe you have some oscillating function, and as you get closer and closer to 0, it just oscillates really wildly near 0. So maybe you get something like that where there's some wild oscillation and you can't compute a derivative at that point. Okay, so that's just some situations where a function isn't differentiable, say if you're looking at a graph. But now let's just talk about higher order derivatives. So consider that just as velocity describes the rate of change of position, acceleration describes the rate of change of velocity. In this way, we're often concerned with derivatives of derivatives. So for example, we might write f prime of x prime equals f double prime of x. And likewise, the derivative with respect to x of the derivative of y with respect to x is the second derivative of y with respect to x twice. So this notation, the way we read this is actually kind of important. When you get into Calculus 3, you'll be dealing with multiple derivatives, and you'll be taking derivatives of multiple variables, and the order that you take those derivatives will matter. So we say this in this way: the second derivative of y with respect to x twice, because it indicates that each time we take this derivative, we're doing it with respect to that same variable. Okay, so we'll just look at a little chart here. So we call the original function the 0th derivative. So in Lagrange notation, we'll write f of x. In Leibniz notation, we'll just write y. For the first derivative, f prime of x, or dy dx. Second derivative, we'll write f double prime of x. We'll write the second derivative of y with respect to x twice. The third derivative, f triple prime of x. The third derivative of y with respect to x 3 times. Fourth derivative. Now here, once we get to the fourth derivative, we start writing this, we'll usually write this like Roman numeral style. All right, so this is the fourth derivative of x, or the derivative of y with, getting myself tongue twisted. The fourth derivative of y with respect to x 4 times, so forth and so on. Now, once we get to large values, typically what we'll do instead is write f parentheses n of x. So this, if I write parentheses, this is the 7th derivative. And it's important that that parentheses is there, because otherwise you mean an exponent, which would be a power, right? So this parentheses tells us it's not a power, it's a derivative. So just keep that in mind. Okay, so a couple more examples here. First, we'll find the second derivative of f of x equal to 3x cubed. So the first derivative, df dx, that's the limit as h goes to 0 of f of x plus h minus f of x over h. This is the limit as h goes to 0 of 3 times x plus h cubed minus 3 times x cubed over h. Now, this multiplication of x plus h cubed, you could write this out long ways, or I've demonstrated how to do this type of binomial multiple in the past with Pascal's triangle. I'm going to skip that step just for time here. But this is going to give me 1x cubed plus 3x squared h plus 3x h squared plus h cubed minus 3x cubed. And then I'm going to go ahead and distribute that 3. So I get 3x cubed plus 9x squared h plus 9x h squared plus 3h cubed minus 3x cubed all over h. And the 3x cubeds cancel. And then I'll factor in h out of the remaining terms up top. So I get h times 9x squared plus 9xh plus 3h squared over h. And now we've removed the discontinuity, so we can plug in h equals 0, and we get 9x squared. But that was just our first derivative, so now we want to take the second derivative of f with respect to x twice. So that means we're taking the derivative of the derivative So this gives me 9x plus h squared minus 9x squared all over h. That's 9 times x squared plus 2x h plus h squared minus 9x squared. Okay, that gives us 9x squared plus 18xh plus 9h squared minus 9x squared over h. So my 9x squared cancels with the negative, and then I'll factor out an h up top. That cancels my h's, and now I'll just go ahead and plug in my 0. I get 18x. So that's my second derivative. Okay, well, we're almost done here. I got one more example I'd like to go through. So we're just going to find the first derivative of f of x equal to x minus 1 over 2x minus 3. So df dx is the limit as h goes to 0 of x plus h minus 1 over 2 times x plus h minus 3 minus x minus 1 over 2x minus 3 all over h. So this one we've got a decent amount of algebra to do. I'm going to try to work a little bit quickly on it, but I don't want to rush it too much. So first thing we're going to do is just expand things out a little bit and rewrite this. This parentheses doesn't have anything happening to it, so we can write x plus h minus 1. And we'll distribute this 2, and we get 2x plus 2h minus 3. Minus x minus 1 over 2x minus 3. All over h still. And now here I want to combine these two fractions together, so I'll just multiply by the missing denominators on each one. Okay, so we're going to get a whole bunch of stuff here. I'll just write out the denominator first, since it'll be the same. Right, they've got the shared denominator, so I'm combining these fractions together. And now we'll write out all this multiplication. So we're going to get 2x squared plus 2xh minus 2x minus 3x minus 3h plus 3. All I did was distribute the 2x across the 3 terms, and then distributed the negative 3 across. Minus parentheses, this negative has to apply to the whole product here. And now I'll distribute the x, and I get 2x squared plus 2xh minus 3x, and distribute the negative 1, minus 2x minus 2h plus 3. And this is all being divided by h. So instead of writing this as divided by h, I can multiply by the reciprocal 1 over h. And now we'll rewrite this again. So this is about as, convoluted as it can get. They don't get much trickier than this. So we'll rewrite the denominator first. I just don't want anyone to ever say that I don't do any of the hard problems. Now I distribute this negative. I get minus 2x squared minus 2xh plus 3x plus 2x plus 2h minus 3. And so now I'm just going to go hunting for things to cancel. 2x squared minus 2x squared. Negative 2x and a positive 2x, and a negative 3x and a positive 3x. And a positive 3 and a negative 3. And a 2xh and a negative 2xh. All right, and we canceled most of that stuff. So let's see what we got left. I got a negative 3h plus 2h. That's a negative h over this whole thing. And a negative h over h is just negative 1. And now when I plug in my 0 for h, I get negative 1 over 2x minus 3 times 2x minus 3. That's negative 1 over 2x minus 3 squared. Okay, so I would say that's about as tough as they're going to get with these limit definition problems. Well, now we're going to take a look at a very important theorem that's going to get referenced quite a bit throughout calculus. And the theorem is very simple in its statement. It's just that if f is differentiable at a, then f is continuous at a. So we're going to prove this, and how do we prove it? I guess I should have written proof here. Maybe add that to your notes. Proof. Well, in order to prove it, we have to show that the limit as x approaches a of f of x equals f of a. That's just the definition of continuity, right? So that's the definition. We can do this by showing that the limit as x goes to a of f of x minus f of a is 0. All right, so that's going to be our first key step. If we can show that, then it's not hard to show that the limit as x approaches a of f of x is f of a. So we're going to start by showing this first thing. Okay, how do we do that? Well, since the problem gives us that f is differentiable at a, we have that f prime of a, which is defined as the limit as x goes to a of f of x minus f of a divided by x minus a, exists, right? That's what it means to be differentiable, is that this limit exists. Next, let's notice that f of x minus f of a is equal to f of x minus f of a over x minus a times x minus a. Now, of course, we're assuming here that x is not equal to a, but that's implied by the fact that when we talk about the definition of differentiability, the definition of differentiability isn't concerned with what's happening at a. It's concerned with what's happening as x approaches a here. So we don't have to worry about x being a and dividing by 0 here or something. Okay, so since we have this expression is equal, we can take limits of both sides of the expression, and we should get the same thing. So if we take the limit of the left-hand side, the limit as x goes to a of f of x minus f of a, is going to be equal to the limit as x goes to a of this right-hand side, f of x minus f of a over x minus a times x minus a. Now, we should recall from our limit laws that if we have a product between two functions, and each of those functions' limits exist, we can split up the limit on that product. And so that's what we've done here. We've split up this limit to the limit as x goes to a of f of x minus f of a over x minus a times the limit as x goes to a of x minus a. Now, this first limit is by definition the derivative of f at a. And this second limit here, the limit as x goes to a of x minus a, has to be 0. Because if x approaches a, you just get a minus a is 0. And so that means this whole thing is 0. So we've shown the first thing we wanted to show, which was that the limit as x approaches a of f of x minus f of a is 0. Now we're going to apply that result to actually show the specific definition for continuity. So if we look at the limit as x goes to a of f of x, we can rewrite that as the limit as x goes to a of f of a plus f of x minus f of a. All we've done here is inside the limit, we've added and subtracted f of a, which means we've really added 0, but we've changed the way we've written the limit here. Now, by changing the way we've written the limit here, we can split this limit on the sum, and we get the limit as x approaches a of f of a plus the limit as x approaches a of f of x minus f of a. Now, since there is no x in this expression f of a here, this limit as x goes to a is the limit of a constant, and so we just get our constant f of a back. And our second limit here we already showed was 0, so that's 0. And that gives us f of a. So altogether, we have that the limit as x approaches a of f of x is equal to f of a, which is the definition of continuity at a. Therefore, f is continuous at a. All right, that's it for this one. Thank you for watching.